Brian. Aswani sir, can you hear me now?
Yeah. Yes, sir. I'm able to hear you. Hello. Am I audible, sir?
Yes, sir. You are audible. Sir, we will start the session. Can you hear me now, sir?
Yes, yes, I am able to hear you.
Yeah. Thank you, sir. We will introduce you formally. So by then we'll hand over it.
Sure. And we started recording, right?
So good evening, one and all. We have come to the last session of the second day. Hope you are all having enriching sessions. It's my privilege to introduce today's distinguished resource person, Dr. Aswani Kumar Cherukuri from WIT Vellore, who is going to deliver a session on post-quantum cryptography algorithms and migration, which is an emerging topic. Dr. Aswani Kumar Cherukuri is a director of Center for Artificial Intelligence Research and professor of School of Computer Science Engineering and Information Systems, Vellore Institute of Technology, Vellore. His research interests are machine learning, information security, and quantum computing. In particular, his work is focused on encrypted network traffic analysis, machine learning techniques. Also, he has interest in post-quantum cryptography. He has 24 plus years of academic and research experience. He published more than 200 research papers and has 5,500 plus citations and H-index of 36 as per Google Scholar. He executed as principal investigator different research projects of worth 10 million US dollars from various funding agencies in India. He has guided 8 PhD research scholars and few foreign interns. He is continuously recognized since 2020 as top 2% scientist in India in the area of AI and ML by a study of Stanford University researchers. He has authored a book on encrypted network traffic analysis published by Springer. He was the adjunct professor of UCSI University, Malaysia during 23-25. Now he is the visiting professor of VCD, Lithuania. He has received awards including Young Scientist Fellowship from Tamil Nadu State Council for Science and Technology, Inspiring Teacher Award from Indian Express, Educator Excellence Award from VMware, etc. He is the editorial board member of several international journals. He is a senior member of IEEE and ACM, vice chair of IEEE Educational Task Force on Data Mining. He is a distinguished speaker of ACM and has delivered several lectures under this program at various institutes. During 2015-18, he served as a Dean of School of Information Technology and Engineering, Vellore Institute of Technology. He has organized international conferences within country and abroad. Also, he actively participates in curriculum development, academic planning, and institutional activities of various other institutes, contributing to continuous improvement in teaching learning process. Now, I request our esteemed resource person, Dr. Aswani Kumar Cherukuri, to kindly deliver the session. Over to you, sir.
Thank you, madam. So, am I audible?
Yes, sir.
Okay, my slides are visible, right?
Yes, sir. Fine.
Okay. So, at the outset, I would like to thank the organizers of this ANRF funded 5-day faculty development program at GVP Institute at Vizag. My lecture would be on post-quantum cryptography algorithms and its migration. So my session would be covering these topics. In the next few minutes, I would be discussing about few fundamentals of cryptography. The reason would be various crypto primitives are to be understood thoroughly before we enter into the post-quantum cryptography. The reason, of course, cryptography per se, when quantum computers comes into existence, meaning commercially deployable quantum computers comes into existence, cryptography is under threat. But at the same time, not that all crypto primitives are under threat. There are certain areas where there is a immediate attention is requiring, and there are areas where the impact would be very, very, very minimal. So in that regard, we need to understand the cryptography in that direction. Next, I would be talking about some of the quantum computing principles, but I'm sure that some of those principles might have not been covered in the earlier sessions. So I will throw some light on some of the quantum computing principles. Then I will discuss about the post-quantum cryptography, which we shortly call it as a PQC. Especially, there are certain variants of PQC algorithms. In my today's lecture, I will be focusing on not on all the PQC algorithms, but rather I will be talking about a specific problem called learning with errors, which is the fundamental unit for post-quantum cryptography algorithms. So understanding the LWE problem, meaning learning with errors problem, is the fundamental for understanding any of the PQC algorithms. So in that regard, I will be touching about post-quantum cryptography algorithms, and in specifically, I will be discussing about the LWE problem. Also, I will be discussing about the one or two variants of the the PQC variants. Then I will discuss about the migration path or plan.
अब तुम देखो बेटा, तुम आओ बेटा, तुम देखो, तुम बताती हूँ मैं। हाँ, पढ़ाने तो नहीं आऊंगी बेटा, देखो भाई मार।
So I will be talking about the migration strategy need to be adopted towards introducing the PQC into the
Be able to unmute your mic, sir. The mic is muted, sir.
Oh, from the beginning it is muted. Okay.
No,
Sorry.
just now, sir. Just now, sir.
Just now. Okay. I think
Thank you, sir.
The few slides, the first few slides you were able to hear, right?
Yes, sir.
Okay.
Thank you, sir.
Right. Thank you. So I will be okay now. So all of us know, in a communication environment, we take these two communicating parties like Alice and Bob as the example. So there is an Alice and there is a Bob. Both are communicating with each other, and Alice is the sender and Bob is the receiver. This is the traditional setup which we discuss in the cryptography environment. Now, when both are communicating with each other, we also know that this particular communication channel, whatever they are using for communication purpose, so either this should be a private communication channel, meaning there are no much threats in the communication channel. So channel is secured, and of course, since it's a private, communication channel would be always secured. But in a practical scenarios, certainly this particular communication channel, what these the sender and receiver are communicating is not a private channel, rather it is an untrustworthy network, meaning an open communication channel. So channel is always open. So best example for an open communication channel, we call it as an internet, where you have always an eavesdropper listening to the communication. So eavesdropper try to gather the information that these two communicating parties are interacting. Obviously, our job is how to make the communication secure so that the eavesdropper, whoever is listening to the communication channel will not be able to get what actually the sender and receiver are communicating. Now the question is, any security principle that is trying to protect the communication cannot remove completely this particular eavesdropper. So meaning your eavesdropper would be there always. You cannot eliminate the eavesdropper. Now, under the presence of eavesdropper, how do we ensure that the communication channel is secure? So that is the fundamental problem that security tries to address. So you have the first motivation. The motivation is that the communication channels are open and you have spies listening to our communication or the data that is being transmitted. And the second motivation is that these eavesdropper are not only acting as a passive eavesdropper, rather they are active, meaning whatever that we are communicating, they are trying to alter it or modify it. So these are the two motivations that we have in mind. How do we secure the communication? Okay, that is the fundamental principle. Now, is it that the security is only for that? But predominantly, when we do research or when we, read literature, we see these two motivations, meaning Alice and Bob are communicating with each other, trying to protect the communication from the unknown eavesdropper, that is Eve. But security is a much larger problem, not restricted to this. What is that larger problem? The larger problem comes, imagine Alice and Bob, they are not trusting each other, right? So meaning Alice is sending some message to Bob and Bob is sending some message to Alice. So one of the security problem is you need to ensure that neither of the communicating parties should deny the transaction. We call it as the non-repudiation, right? This is one of the security challenge, right? Which generally explicitly people do not discuss very frequently. But this is one of the fundamental problem, non-repudiation. There is another problem. Other problem is that how that authentication can happen between both Bob and Alice. So how do each other authenticate themselves to each other? So user authentication, that is another motivation. So meaning when you list out the motivation to secure the communication, you have so many things, not only just protecting the communication from the eavesdropper, but rather authentication, non-repudiation, and etc. So like this, when we list out all the security goals that what we have, you will come across number 1, confidentiality, number 2, integrity, number 3, availability, number 4, authentication, and number 5, non-repudiation, right? So these are the 5 security goals that one has to achieve in the communication channel, or when you have having a data to be protected, information assets to be protected. These are the pillars of security. So confidentiality means ensuring only the authorized parties will be having access to the data. Integrity meaning the data is modified or altered only by the authorized people. No unauthorized entity would be able to do the alterations. That's what is the integrity principle says. Availability means all the authorized people should be having access to that particular information resources at all times, or at least whenever they need it. That's called availability. Other aspects are like authentication, where you have to verify identity of the users, not only users, but also the devices, systems, processes. This calls even messages. This called authentication, right? Then non-repudiation, just now I said about preventing communicating parties denying the transactions, denying the actions that they do. So meaning this comes when you have no trust environment, right? When there is no trust between the communicating parties, you have to handle the problem of non-repudiation, right? So when you look at the others like confidentiality, integrity and all, essentially about to protect the trusted users from eavesdroppers and masqueraders other entities, right? So this is about the fundamentals of security goals. Now, how do we ensure that? Obviously, you need to go for cryptography. So the fundamental aspects of cryptography is especially in the lies with the confidentiality, where you can achieve this confidentiality through encryption principles, right? That is one way of achieving confidentiality. There are other ways of achieving confidentiality, including access controls, key management, key generation and storage, providing security to the endpoints, ensuring that there is no data loss, and then application of cryptography at the network security level through TLS protocol or VPN, etc. So confidentiality can be enforced through this means. But for all that, the bottom line underlying mechanism is encryption, right? So the encryption, if you have observed in the previous image, encryption predominantly has two types of mechanisms called symmetric encryption and asymmetric encryption. The symmetric encryption is the means in which when you have two communicating parties, right, when they are communicating with each other, they use the same key for encryption purpose and the same key for decryption purpose. Meaning, when Alice is sending a message to Bob, message called M, Alice would encrypt that message with the help of an encryption key called K, and the output is called ciphertext that would be sent to Bob. Bob would decrypt that ciphertext with the help of same key K to get the message back. So since the same key is used for encryption and decryption purposes, we call that encryption as the symmetric encryption mechanism, right? So there are various symmetric encryption algorithms that we have. Predominantly, you have advanced encryption standard AES 128, 192, AES 256, blowfish algorithm. Of course, there are some very old deprecated algorithms such as data encryption standard, triple DES, etc. These are all for the block ciphers, meaning the plain text message M would be divided into multiple blocks. So each block would go for encryption, and hence it's called block cipher. Instead of the message is going as a stream mechanism, that is called stream cipher, meaning alphabet by alphabet. When you encrypt, it is called stream cipher. Even for stream cipher encryption, you have different algorithms for symmetric encryption purpose. Now, when you look at this philosophy of symmetric encryption, both the sender and the receiver are using the common key, the same key for encryption purpose and decryption purpose. This encryption algorithm is predominantly fast. However, the point is, or the challenge lies in this particular mechanism is that how both communicating parties will have the common key. Right? How do you establish common key between communicating parties? Meaning, in symmetric encryption algorithm, key management and key distribution are the challenges, because both communicating parties should have common key. How do we ensure that both will have same key for encryption purpose and decryption purpose? So in order to mitigate this particular challenge with the symmetric encryption, you have asymmetric encryption algorithms where you are having two keys. One key is known as public key, another key is called a private key. Meaning, when you have two communicating parties, Alice and Bob, when they are communicating with each other, Alice will have her public key and her private key pair. Bob will have his public key, and his private key pair. So every communicating party will have their own key pairs. So when Alice is sending a message M to Bob, what Alice would do, Alice would encrypt that message. Alice would encrypt the message M with the help of public key of Bob and send it that ciphertext to Bob. What Bob would do, Bob would decrypt that ciphertext with his private key so that he get back the message. When you closely observe, this encryption mechanism is using public key of the receiver for encryption purpose and private key of the receiver for decryption purpose. Since decryption is done with the help of private key of the receiver, no one else can decrypt that particular message. That is the beauty of this algorithm. So you are able to encrypt with one key and you are able to decrypt with another key. Remember, in this case, the sender public key, private key are not used in this particular mechanism, right? When Bob is sending a message to Alice, in that scenario, Bob would use Alice public key. Since we are calling that key as the public, Bob would know Alice public key and Alice would know Bob's public key. Alice certainly would not know private key of Bob. Bob would not know what is the private key of Alice. So that is the mechanism of asymmetric key encryption. Now, in this scenario, there are certain algorithms called RSA algorithm, elliptic curve algorithm, then Elgamal algorithm, Diffie-Hellman algorithm. These are all the examples for asymmetric encryption. When you look at these algorithms are quite slow when compared with the symmetric encryption. The slowness is because not to perform encryption. The slowness is because of generation of the keys. So first of all, how do we generate such keys, two keys, in a way that you should be able to generate two keys in a way that one key is used for encryption purpose and the another key is used for the decryption purpose. So how do we create such type of keys? That is where the asymmetric encryption algorithms are quite slow when compared with the symmetric encryption algorithms. Now, if you go back again to this particular phenomena, what I said about the sender is using receiver's public key and receiver is using his private key for encryption purpose, will ensure confidentiality, right? This ensures confidentiality. I said sender's key pair is not used. Of course, if you want, you can use. Meaning what happens when you have a sender and receiver, public key of Alice, private key of Alice, public key of Bob, private key of Bob. Now I'm writing a different scenario where message M is encrypted with the help of private key of Alice and the ciphertext C is sent to the receiver. Receiver will decrypt it with the public key of Alice to get the message. Now this scheme is different and this scheme is different. In this case, we have used receiver's public key for encryption and receiver's private key for decryption. And in this case, we have used sender's private key for encryption and sender's public key for decryption, right? So if you closely observe, this ensures confidentiality, but this will not ensure confidentiality because anybody can decrypt this particular ciphertext C with the help of public key of Alice, because Alice public key would be known to everybody, including the attackers. Now you may ask a question in such scenario, why this particular mechanism is required? This is required when you need authentication. Meaning, if you observe this first scenario, you are able to get confidentiality. Anybody who knows Bob's public key can send a message, an encrypted message to Bob, but Bob do not know who has sent the message. Because encryption is done with the help of public key of Bob. Anybody can encrypt it. Now Bob do not know who has sent the message because decryption is happening with the Bob's private key. Now look at this scenario. Encryption has happened with the private key of Alice. Now decryption should happen with the public key of Alice. Now when Bob is decrypting this message, Bob has to use Alice public key, meaning Bob now knows for sure that this message has come from Alice. So authentication is happening. So meaning what? If you want confidentiality, go for encryption with the public key of receiver and decryption with the private key of receiver. If you want authentication, encrypt with the private key of sender, decryption with the public key of the sender. So asymmetric encryption is giving you the both options of confidentiality and as well as authentication. Of course, both can be combined by performing double encryption, right? So you can achieve both confidentiality and authentication. I think my flow of talk is fine, right?
Yes, sir. Yes, sir.
Now, with this encryption algorithms, we have all protocols every day we are using. Predominantly, the most, every day we dependent on this HTTPS, starting from our Gmail, banking transactions, everything. This particular, the transport layer protocol, HTTPS, hypertext transfer layer, using the TLS protocol, your HTTPS is providing security to all our web-based communications. Now, imagine I wanted to connect to a particular remote systems using remote desktop privileges. You have SSH, which is providing an encrypted communication channel for remote desktop access. Secure file transfer, which is providing file transfers on top of SSH, right? Then you have, the email security being provided using, the so far whatever we talked about symmetric and asymmetric communication techniques. Similarly, the TLS, transport layer security, which is which is the backbone for your HTTPS. These are all actually the security protocols that are there in your TCP/IP protocol stack of application layer, your transport layer, and as well as on the network layer, right? All these protocols, are leveraging your encryption techniques so that communication in these different layers of your TCP/IP protocol stack are secured. So when we have seen this, the essentials of the symmetric encryption and asymmetric encryption, we said that you have to create the key pairs, right? Public key of Alice and then private key of Alice. Similarly, public key of Bob and private key of Bob. So how do we actually use this create this such type of public key and private key pair? What is the mechanism, right? In fact, this is what the reason why the key generation is the mechanism why your algorithms are quite slow. The Alice uses certain algorithms where you use a large random number generation algorithms and then also use prime factorization algorithms. Finally, you get a public key of Alice as well as private key of Alice. Down the line, we have an algorithm called RSA algorithm that is essentially creating public key and private key pairs, right? So once you have this, what you can do is, as I have said, Bob can take the, the Alice public key, and then this is your message, encrypt with the help of public key of the receiver. In this case, I said, of course, in my example, I said Alice is the sender, Bob is the receiver. Now, this slide is talking about Bob is being the sender and then Alice is the receiver. So Bob is sending a message using the Alice public key, encrypt it, and at the end of communication, Alice would take it, decrypt with the Alice private key. So this is how the communication happens. And then not only that, the essentially in a practical scenario, the public key mechanisms are not only used for just for encryption purpose. Rather, one of the challenge that I have mentioned that your symmetric encryption algorithms is to exchange the, how do we have a common key between Alice and Bob in the case of symmetric. So asymmetric encryption algorithms are used for the purpose of sharing of the symmetric keys, right? If you can see here, Alice is taking Bob's public key and Alice will use her private key and combine both of them so that they create a shared secret, right? And similarly, at the Bob side also, Bob uses Alice's public key and Bob will use his private key to create a common key which is a shared secret. Now, if you notice, by combining at both sides, Alice side, you are using Bob's public key, Bob side, you are using Alice public key, and Alice is using Alice private key and Bob is using Bob's private key. When both are combined, they are able to have a common key. Now, if you notice, both are having common key K, right? In fact, this communication, this K is not being shared over the communication channel. Rather, both sides, they are being, derived. So this is the another use case of asymmetric encryption, right? How do we establish the common key in the case of symmetric encryption, right? So once this common key is established, now both parties can communicate using symmetric encryption, right? Because now you have your fundamental problem of symmetric encryption is solved, right? And then, you can, as I said, you take Alice confidential data and then encrypt with the common key K and then send it to Bob. Bob can decrypt it with that common key and get back the message. So use the symmetric encryption, meaning you are using asymmetric to share common key K, right? That is symmetric key, right? So asymmetric encryption algorithms usage, when you look at, not only just for the plain message encryption and decryption, rather in all practical scenarios, predominantly it is used for the purpose of exchange of the symmetric key K, right? Why I'm not going for asymmetric encryption based for the messages? Obviously, the reason is that we have said that asymmetric techniques are very, very slow because of generation of the keys, public key, private key pairs, right? And this is all about, the one part of encryption algorithms. Now you have another part of encryption algorithms called signatures, right? Now we all listen in the digital world concept called digital signatures, right? The digital signatures, if you notice, the prerequisite for the digital signature is that, when Alice is sending a message to Bob, so this is the message M. Now this is the Bob side, the message has to come. There is an eavesdropper who can modify the message. Now Alice's job is to protect that message by signing over the message. So for that purpose, Alice is using her private key, right? Alice is using her private key, and of course, Alice is having her public key and private key pair. Alice is having her public key and private key pair. So what Alice is doing, she is signing over the message using her private key, and anybody who can take the message can verify with the help of public key of Alice, right? So signature, if you notice, digital signatures, if you notice, asymmetric encryption algorithms are used in the way that signing of the message is happening with the help of private key of the signer, and verification is happening with the help of public key of the signer, right? So this is another, the security mechanism in the cryptographic world, right? So if you notice, no one can produce the signature. The reason is the signature will be produced only by the signer, because you are using private key of the signer. Signer only knows her private key, right? Modification anybody is doing over the message can be easily caught, because altering the message will nullify the signature, right? So because of that, digital signatures are used for the purpose of ensuring the integrity, right? I'm not going to touch the RSA algorithm in detail, but having said your digital signatures, asymmetric key encryption algorithm, for all these algorithms, the fundamental philosophy behind these algorithms is the RSA algorithm. RSA algorithm is basically working on one particular mathematical problem called difficulty to factor the large prime numbers. Meaning, I can tell very simplistic terms. Imagine you have two numbers called M and N. If somebody is asking you to find the product of them, it is easy to get the product of these two numbers. But this is easy to get. But imagine if somebody gives you this number T, asking you to find what is the factors of this T, meaning what are these M and N numbers? If somebody is asking, this is called finding the factors, right? Finding the factors is computationally challenging, but finding the product is computationally easy, right? And it is not that you find only just factors of a number, but rather these two numbers are supposed to be the prime numbers. Okay, these two numbers are supposed to be the prime numbers. So finding prime numbers, prime factors of a given composite number is computationally infeasible problem. Based on that, your RSA algorithm is built upon. And of course, when I say RSA algorithm, not for 2-digit, 3 digits that are there in the books, typically 1024, 2048 bit length numbers. When you have such long numbers, how to find the prime factors is the computationally challenging. So take an example, if you have a 2048 bit number, a number would be looking like this. Now imagine if somebody asked you to find what are the prime factors P comma Q for this particular number, it is computationally infeasible for us, even for a supercomputer. But now this particular type of, the challenge is providing the backbone for security of asymmetric encryption algorithms. But however, with the introduction of quantum computers, that particular problem of finding the prime factors is becoming easy. When finding these prime factors becomes easy, your RSA algorithm would no longer be secure. Meaning what happens? When RSA algorithm is no more secure, entire your asymmetric communication, asymmetric encryption algorithms would no longer be secure, right? So that would not help us to provide one fundamental, one fundamental use case. What is that use case? If RSA algorithm is failing, we will be losing one fundamental use case. Can people who are listening, can somebody type in the chat window? What is that we miss? If RSA algorithm is failing, so far I said, what is the use case of asymmetric encryption algorithms? So if your RSA algorithm is failing, we will lose something. What is that? Can somebody type in the chat window? No, not prime numbers. I said, when you are having your symmetric encryption algorithms, the challenge is how do we have a common key, right? So how to establish the common key? That is done with the help of asymmetric encryption algorithms. So if asymmetric encryption algorithms are no longer providing security, you will no longer be able to provide a common key between two communicating parties, and hence you will not have an even symmetric encryption philosophy, right? That's where this RSA algorithm, compromise over the RSA algorithm will hit. Not only that, your digital signatures would be at risk, right? All these things would be at risk, right? So not only that, you have another cryptography primitive called hash functions, where we take a message, right? In cryptography or literature, you have a message M. So we have a hash function, which is a one-way function, where we take the message and then apply over the hash function to get the digest of the message, or we call it as a hash of the message. This is essentially used for the purpose of to check the integrity of the messages, right? These are all various crypto primitives. Of course, digital certificate, if you notice, generally you have a certificate authority. Communicating parties will share their public keys to the authority. Authority will sign the certificate with the help of private key of authority, so that now Alice will have her public key certificate. Bob will have his public key certificate. Both will share their certificates, right? Now, if you notice, the certificates are issued in the name of public key of these users, and it is signed by the private key of the authority, right? Meaning anybody can verify. So this is another use case of the asymmetric encryption algorithms. Of course, there is a difference between digital signatures and the digital certificates, right? And as well as their use case also differs, right? Digital certificates we will find in all our systems predominantly, right? I will skip all this part because we will focus on the essentially the quantum philosophy, right? Now, with the introduction of quantum computers, these mathematical problems, especially the prime factorization problem on which your RSA is based upon, or the discrete logarithm problem on which your elliptic cryptography is based upon, all these encryption algorithms or techniques are no longer secure, right? Now, so as I said in the beginning, I will just spend 1 or 2 minutes on I will talk about the quantum philosophy. The quantum philosophy is gaining more and more popularity. Yeah. So quantum is becoming more and more popularity because of certain particular features. If you notice, in the philosophy of quantum computing, we no longer deal with just real numbers like a classical computers, we deal with the complex numbers, right? The computations happens in the complex numbers. Similarly, we move from single state of the the bits and registers to the superpositions of the bits and registers. We move from computing over locality to non-locality based computing. Similarly, we compute not with the deterministic laws, but rather we compute with the probabilistic laws. Similarly, we deal not just with certainty in the computing, but rather with the uncertainty. These are all the certain features of the quantum world, which makes the quantum computing more attractive to solve certain problems that are not solvable by the classical computers. When you notice, we don't have superpositions of states in the classical computers. We don't deal with the probabilistic based outcomes in the classical computers, right? We don't deal with the uncertainty in the classical computers. Of course, there are other uncertainty related mechanisms, but here what we deal with the uncertainty is totally different. So these laws makes a detailed discussion on these laws are already there in my other recorded lectures. I would actually suggest you, those who are interested, to look at those lectures. What are all these features in detail I have discussed, right? So you have the difference between classical computing and quantum computing, and I'm sure that either in the earlier lectures or in the lectures that are come, you know the differences between the classical computers and quantum computers. You have the fundamental philosophy is that you have either 0 or 1, whereas in the quantum you will have the quantum bits where it is going to be there in multiple states, not just 0 and 1, rather between infinite possible states between 0 and 1, right? We all know that between 0 and 1, you have infinite possible states. So a quantum bit, qubit, would be there in any of these infinite possible states, right? And not only one qubit, when you have multiple qubits, you have all qubits being there available. So take an example with 2 qubits, you will have all possible combinations, meaning ket 00, ket 10, ket 01, ket 11 being available at a time, right? So meaning all these states, your quantum gates would work in parallel. Unlike giving 00, if you are having an AND gate 000010100111, rather here you will have operation on all the states in parallel, right? That's what is the beauty, right? And hence, if you notice, imagine that if you are having a 64-bit computer, what you can do is that 64-bit binary numbers at a single time. But rather, if you have a quantum computer with 64 qubits, what you are going to do is 2 power 64 multiple states you are going to have in parallel. So meaning 2 power 64 means, you can see the number of states that you can have in parallel that is available at a single point of time. that gives a massive parallelism, for computation purpose. Now, in addition to that, you have a superposition state, right? Being being a single qubit being there in multiple states, right? So that is called superposition, right? In case if there is a 3 qubit system, this is called a superposition of all possible states of a 3 qubit system, right? 1/√8 ket 0002 ket 111, right? So of course, this is the scenario. What is given is the equal superposition. It need not be always, right? Similarly, you have another fundamental principle of quantum called entanglement between the qubits, where you can have qubits being entangled together, right? So 2 qubits can be entangled together. 2 qubits can be entangled together, meaning measurement of 1 qubit will influence the other qubit. So these are all the various principles of quantum computing, and this makes, to solve certain problems, which, like, say, take an example, kind of a traveling salesman problem to identify the best route. In a traditional computer should actually explore all possible routes one by one. Rather, a quantum computer can at a time, explore all possible, the paths at a time. So that's what is the beauty or the computing power of quantum computing, right? So, we all might have seen, how these quantum computers looks. There are multiple ways these quantum computers are built, through, photon-based quantum computers, then ion-trapped based computers. Then, of course, superconducting, based quantum computer is the one which we predominantly see in everyday news. This is how a superconducting quantum computer looks. What I suggest is, you can even actually Google what actually that lies within this particular chandelier of a superconducting, qubit, quantum computer. This is where actually the QPU chip lies. The whatever is a tiny qubit chip, whether it is a 5 qubit chip or a 6 qubit chip or maybe a 10 qubit chip. That's what actually looks. That would be there at the bottom, but on the top you can see there are several the wiring and cooling mechanisms, heat exchanging mechanisms that take care of controlling this particular small, the QPU environment, right? So of course, you have quantum gates that are building blocks of quantum computers, starting with the Pauli, etc., Pauli gate, Y gate, and all. Then when you connect all those gates, what you get is the quantum circuits, right? Those who wanted to learn the algorithms also need to learn quantum Fourier transform, quantum phase kickback algorithms, quantum phase estimation algorithms. These are all the techniques that are essentially needed to understand any of these, the quantum algorithms. When you say quantum algorithms, you have popularly, the Grover algorithm, which is providing, enormous potentiality in addressing a problem called unstructured search, right? Imagine if you have a n number of entries. If you want to search over that n number of entries, it takes about an average of n/2 in the case of a classical, whereas a Grover algorithm, which is a unstructured search algorithm, quantum algorithm, that helps us to solve it in the root n steps. Of course, this algorithm impact symmetric encryption. The reason is that, the symmetric encryption is based on common key between the communicating parties. So this particular key, which is typically common key between the users, can be somebody can make a brute force attack to search over the all possible keys with the help of Grover's algorithm. Of course, what is the alternative for this is to increase the key space. That is the one of the possible alternate if to mitigate the Grover's algorithm. But rather now you have the Shar algorithm that is taking care of that is impacting the the asymmetric encryption algorithms by solving prime factorization problem, right? Again, those who wanted to learn about the Shar algorithm, the Shar algorithm actually is trying to solve a particular problem called period finding problem. Again, this algorithm I have explained earlier in a couple of my earlier lectures. So those who are interested, again, my request is to check those algorithms. There are those lectures that are available in my YouTube channel. So this is the algorithm for period finding. how this period can be found. And there is an example also I have given. So those who are interested to learn SHAR algorithm, please look at that, right? So again, I'll skip that. I will go directly to the impact of these algorithms, and then post-quantum cryptography, and essentially what are the various variants we have. So in order to mitigate the threat from the quantum computing, we have 4 variants of post-quantum cryptography algorithms. Essentially, remember, these algorithms are called hash-based algorithms, multivariate algorithms, code-based algorithms, and lattice-based algorithms. These algorithms, they are not meant to run over the quantum computers. They are meant to protect. They are meant to protect the classical computers from quantum threats, right? Meaning, later on, down the line, at the moment, people are expecting that by 2030, 2035, you will have cryptographically relevant quantum computer, meaning a quantum computer that can break all the asymmetric encryption algorithms. If it comes, how do we protect all our classical computing environment from the quantum threats? These are the 4 multiple variants. Now, among these 4 variants, what the United States NIST has come out is these 3 standards called FIPS, Federal Information Processing System Standard, FIPS 203, 204, and 205. These are the current standards which are approved by NIST. Among them, if you notice, FIPS 203 stands for MLKEM, FIPS 204 stands for MLDSA algorithm, and then 205 stands for SLH DSA algorithm. MLKEL algorithm, as the name of it is, module lattice key encapsulation mechanism. MLDSA algorithm is module lattice digital signature algorithm. SLH DSA algorithm meant for stateless hash-based digital signature algorithm. Now, if you notice, among these 2 standards, these are for digital signatures. These 2 are for digital signatures. FIPS 204, FIPS 205 are for digital signatures. And this is for key encapsulation, meaning key exchange purpose. When I say key exchange, which key? That is the symmetric key. A few minutes back also I said, you have a fundamental challenge with the symmetric key encryption algorithm that is solved with the help of asymmetric keys. But asymmetric keys are now in danger because of quantum. So the new NIST standard is proposing, or already has proposed, tested, verified, validated, and now we have programming libraries for module lattice key encapsulation mechanism. Now we will see quickly. So the key encapsulation mechanism FIPS 203 is based on module lattice key encapsulation technique. So let us see what is that particular technique. So essentially, it is used for key exchange purpose, and it is allowing 2 communication parties to agree a particular shared secret over untrusted network. And hence, what does it mean? It is helping to solve your symmetric encryption key exchange problem, right? So once you have a key exchange, then you can do symmetric encryption with the help of AES. So this is what exactly is the purpose of your replacing, your asymmetric communication algorithms such as RSA, Diffie-Hellman, elliptic curve, etc. Right? This is going to replace that. So how actually it is doing? At a conceptual level, what happens when you have a communicating parties? First of all, the server generate its public key and private key pair. Now, what client will do? Client uses the public key and encapsulate a shared secret. So this is the shared secret client has created to share with the server. And it encrypts, rather it encapsulate with the help of public key of server, right? Now, what server will do? Server receives it and it encapsulates it using the private key of server. By doing it, what will happen? The shared secret would be now also with the server, and hence both are now having the same secret. If you observe, server is also having now public key and private key. Remember, earlier public key, private key pairs are used with the help, are created with the help of RSA. Now they are created with the help of the structured lattices and a concept called noise-based encoding. Now we will see what is that structured lattices and noise-based encoding. Before that, where it is being used, this module lattice-based key encapsulation mechanism is used in TLS handshakes, meaning your HTTPS protocol. It is also used in VPN. It is used in the secure messaging protocols and etc. Wherever current asymmetric encryption algorithms are there, your MLKEM comes into picture. We will see first that particular what is MLKEM. Before that, the MLKEM is based on a particular problem called learning with errors. To introduce learning with errors, let us all see one particular diagram that is shown in the screen. Imagine you are having a geometric structure that has multiple corners, A, B, C, 2H. These are all the corners, right? Now, imagine I have a point called A. I have a point called A. Now, there is a question is asked to which of the corners A to H on this particular geometrical structure, this particular point is closest. Is A is closest to D? Is A is closest to B? Or is A is closest to F? Or A is closest to H? How do we answer this question? So please think for a moment. You have a geometric structure having multiple corners. I have taken a point and I wanted to know this particular point in the geometrical structure. This particular structure is a cube, and to which corner this particular point is closest. If somebody asks this question, how do I answer this? In order to answer this, I need to know, first of all, where this particular point is located. Is it located inside the cube? Or is it placed on the front side of the cube? Or is it placed at the back side of the cube? Right? So you do not know what is the exact position of this particular point on the cube. Why you do not know, or why I do not know? The reason is that when I am looking at this particular structure, it is a two-dimensional structure I am seeing, but rather actually the structure is a not two-dimensional structure, it's a multi-dimensional structure. But when I am looking at it, it's only a two-dimensional structure. Meaning what happened actually, your original dimensionality is higher, but when I am projecting, I am seeing only the lower dimensional structure, meaning there is a loss of information. When there is a loss of information, I'm not able to predominantly tell to which point or to which corner this particular point is closest. So now why we are discussing this? We are discussing this. The reason is that we are trying to build a cryptography algorithm that is not solvable or not crackable even by a quantum computer. Your classical encryption algorithms are based on problems which conventional computers cannot solve, like time factorization, like solving discrete logarithm problem. Now, meaning we need to choose a problem that cannot be solvable by even a quantum computer, right? So finding the shortest vector, finding the closest vector in a lower dimensional space of a higher dimensional geometrical structure is a problem that even the quantum computers cannot solve. Okay, so that is where your entire PQC algorithms, whatever we talked about, lattice-based cryptography, hash, the multivariate cryptography or code-based cryptography comes into picture. They use this particular phenomenon called not able to solve a shortest vector problem or a closest vector problem in a higher dimensional structure when you have a lower dimensional information, meaning with a loss of information. That is the fundamental problem on which entire PQC modes of algorithms are based upon, right? So because of that, it is impossible for us to derive a single correct answer by just visual inspection over the geometrical structure or even by any mathematical tool to tell to which corner this particular point is closest. And this particular hardness of the problem makes certain class of encryption algorithms that are not solvable by the quantum computers, right? So this is where actually your lattice-based cryptography comes into picture, right? Now I will also cover this cover the problem of LWE connecting with this particular problem of finding the shortest vector or finding the closest vector. What is LWE? I said LWE stands for learning with errors. Okay, learning with errors problem. What is that learning with error problem? I will be for the next few minutes I will talk some mathematical terms. The first mathematical term I will talk is called lattice. What is a lattice? Lattice is a set of points, and it is set of points in n-dimensional space, and these points are separated with the periodic structure. So the lattice is a set of points and they are in the n-dimensional space, and these points are separated with a periodical structure, meaning if you see the distance, it's a periodic structure. Since these points are separated in a periodical structure, you have this set of points are being called as the lattice. Okay, how do you define mathematically? Mathematically, the lattice is defined as some linear integer combinations of independent vectors. I have n independent vectors, a1, a2, so on, n independent vectors. Remember, each vector is of some m dimension. Okay, each vector is of m dimension, and I have totally n number of vectors. I have totally n number of vectors a1 to an. So now what is my lattice? My lattice is this a1, a2, so on, n independent vectors and their coefficients x1, x2, so on, xn. These are all called coefficients. These are all coefficients. So my lattice is a set of independent vectors along with their integer coefficient is called a lattice, right? So these independent vectors a1, a2 to an are each are of m dimension, right? So that is the reason why if you notice my lattice is m dimensional lattice space, and I have n number of lattice points, and hence the rank of the lattice is n. So I have m dimensional lattice, right? Since I have n number of such vectors, rank of lattice is n. Okay, right? That I need to I need to understand that. Similarly, all these coefficients x1 to xn, they are coming from set of integers, right? So this is the mathematical philosophy that we need to keep it in our mind. Now imagine I don't take n number of the vectors. Let me take only two vectors. What are the two vectors? a1, a2, and they have two coefficients x1, x2, right? Now you can see that my lattice is in the two-dimensional space. Why I am calling two-dimensional space? Because a1, a2 are of two dimensions, right? Now, since I have two vectors, my rank of the lattice is also 2. Now, if you draw that lattice in a graph point, I can see that these two vectors I have a1, a2, right? So this is how it looks when I have a simple two-dimensional lattice, right, with a rank 2. What we have seen is the m-dimensional lattice with n number of vectors. Just for visualization purpose, we have taken 2 vectors. Now, okay, do I have to geometrically see? Of course not. I can also represent that in the form of a matrix, right? Let me take a small example of a lattice, which is defined over set of integers called Z17. Remember this, if you observe, this is a prime number, right? So that's the reason why I'm calling it as ZQ, where Q is your prime number, right? And my lattice rank is 4, meaning you see here I have 4 vectors. Okay, and each vector is of dimension 7. So you can notice 1, 2, 3, 4, 5, 6, 7. So I have 7 dimensions for each vector, and I have totally 4 such basis vectors. This is A1, this is A2, this is A3, this is A4, right? So I'm representing that lattice in the form of a matrix, which is Z17, meaning entries of this matrix are coming from Z17, meaning numbers below 17, right? 17 is my prime number, right? And the size is 7 cross 4, meaning 7 is the dimension, 4 is the rank, right? I can write it as A, or I can write it as a transpose. So lattice, I'm representing geometrically, I am representing in the form of a matrix as well, right? Next, as I said, I have the basis vectors of the lattice A1 to AN, right? When you multiply them with the coefficients, earlier slide I said x1 to xn, and now I'm calling them as s1 to sn. The simple reason is that my integer coefficients are nothing but secret integers. So s1, s2, sn, these are all secret. Okay. So when I have n basis vectors and their integer coefficients s1 to s7, sn, when I perform, a multiplication between the coefficients, and when I do the addition of all of them, I get a target. Okay. And this point is also on the lattice. So how do I write that? S1, A1, so on, Sn, An is the T. Right. Now, an adversary is now, meaning adversary means an attacker is now given the starting point. Meaning, what do you mean by starting point? Set of all basis vectors A1 to AN, as well as end goal called target. What the attacker do not know is the secrets S1 to Sn. So what the attacker is trying to do, he is trying to find the value called set of integers S1 to Sn. So what he has, he has the basis vectors AN to AN, and he also having the target, which is the point on the lattice, but he do not know how to reach this target point. For that purpose, he has to calculate S1, S2, so on, Sn, right? How do we do it? First of all, how to write that in a mathematical term? A dot S is equal to T. A is your set of basis vectors, S is your secret integers, T is your target point. Solving this equation is nothing but A dot S is equal to T. Attacker knows A, attacker knows T. Attacker has to calculate the S, that is the set of integer coefficient, right? Take an example this. Imagine you have a lattice like this, the example that we have considered earlier. So A dot S is equal to T. When you notice A is known to the attacker, T is also known to the attacker. The attacker do not know the S, right? Now, how to solve this particular problem for this? Of course, S is nothing but, this S vector is nothing but the solution is this. Attacker can easily calculate this problem. How do he calculate this problem? By performing Gaussian elimination method, right? There is a technique called Gaussian elimination technique to calculate S in the equation A dot S is equal to T when A and T are known to the attacker, right? Now, how do I make this problem complicated? This problem can be made complicated by introducing an error term. What is that error term? Imagine the issue is coming because the resultant vector T is point on the lattice. But imagine T is not the point on the lattice, but it is a point that is close to some other point on the lattice. How do I make that point T to push out of my lattice or make it closer to some other point on the lattice rather which is directly on the lattice? For that purpose, what I'm doing is I'm modifying that A dot S is equal to T as A dot S plus E is equal to T transpose, right? Earlier my expression is this, now current my expression is this. What I did, I have introduced a term called E. What is this E? E is nothing but my error term, right? So now how this my expression has become, this is my, my lattice, this is my secret coefficients, this is my error term, and this is my target. And of course, I have taken the, my prime number as 17, so mod Q, right? Every operation that is being done in the arithmetic operations that happens at mod Q, mod prime number. So now the attacker knows only A, not only T, he has to calculate S and E. So meaning he has to calculate the secret, he has to calculate the error, right? So that makes attacker not able to compute the correct solution since T dash is not the point on the lattice. Why T dash not on the point on the lattice? Because you've introduced the error term that pushes this, the point beyond the lattice structure. So anybody wants to find out, he has to find where is this point. That's what is the philosophy called learning with error, right? LWE problem, right? So this target vectors, if you notice, in the earlier case, this is your A dot S is equal to T, and this is A dot S plus E is equal to T dash. If you notice, in this particular example scenario, between T and T dash, you can see that they are very close to each other, right? Now you can see that elements in the vector T and T dash, this is 2, this is 1, this is 14, this is 13. So meaning you can see that the error is a small deviation, right? This is a very small deviation ranging between -1 to 1, right? It's not a larger deviation. The larger the deviation, of course, I can take a larger deviation, but the problem I would face is for my legitimate receiver, that becomes harder to decrypt. No, my purpose is not to make the actual receiver to suffer, right? So I keep my deviation small enough such that I keep this deviation error small enough such that for an attacker, it is intractable. For a legitimate user or a legitimate receiver, that is tractable, right? So this is the problem called LWE. So if you can notice, the error term, is the error. This is your error vector, right? So this is the problem called LWE problem, based on which, all our, the PQC algorithms are based upon, right? So now the point is, how do you formalize this LWE problem? This is the formal definition of LWE problem. And for that purpose, in order to practically implement, all your messages are first have to be converted into the, they need to be encoded into the, LWE problem. So for that purpose, you have an encoding mechanism. This is your encoding mechanism. And since you have an encoding mechanism, now of course you should also have a decoding mechanism at the receiver side. This is the decoding mechanism. So this particular problem, what I have said, is used for the purpose of generation of the key. So you can see first that any encryption and decryption algorithm with LWE will have 3 fundamental principles. One is called key gen, another one is called encryption, another one is called decryption. So you can see that LWE key generation, if you see, the output would be your target and your lattice structure, right? So you can see that, the algorithm for key generation takes some n random vectors and combining them into a form of a lattice, or, you can think of as a matrix. Then take the random secret S small integer values, then build the random vector E with the small integer values, right? Compute your T is equal to A dot S plus E. And what happens is your T comma A becomes public key. And of course, your secret set of coefficients forms your private key. And with that, we go for encryption purpose. Of course, encryption, as I said, encryption is done with the help of public key. So public key in the previous slide, we said T comma A is your public key. And then output would be two things. Those who are familiar with the Elgamal encryption algorithm in regular asymmetric encryption algorithm, they can very well easily understand the purpose of auxiliary ciphertext and also the actual ciphertext. So this is your encryption algorithm. Then subsequently, you have a decryption algorithm. The challenge with this LWE, simple LWE problem is that it performs encryption bit by bit. Okay, but of course we said, you have a blocks of text to be encrypted or the numbers to be encrypted. So for that purpose, the LWE, simple LWE problem is extended to address this multi-bit encryption, expanding the ciphertext, and to handle the larger keys. Simple LWE scheme, what I have discussed, is extended to ring-based learning with errors problem, where in which we don't take a set of simple integers, rather we take a set of polynomials and their coefficients form the entities of the lattice structure. So that is the extension to the standard LWE problem. So ring-based learning with errors. Combining this simple LWE and ring-based LWE, you have module-based LWE, where in which you have a matrix coming from single or standard LWE. Elements are coefficients of the polynomials, right? Elements are the coefficients of the polynomials. That's what is the module-based learning with errors. Now, what are all the PQC schemes that we have said, right? MLKEM, MLDSA are based on this particular philosophy, right? Digital signature algorithm, key encapsulation mechanism of PQC are based on this particular philosophy, right? So this is where LWE problem is providing the basis for PQC algorithms, right? So your MLKEM and MLDSA are based upon your learning with error problem, right? So next we have the digital signature algorithm coming from hash-based digital signatures, right? That also I will quickly touch upon, so that today's discussion we will have a complete this thing. So your digital signature algorithms, especially coming from stateless hash-based DSA, is not based on the lattices what we have seen. Rather, it is based on the hash functions, especially those who are familiar with cryptography. Of course, I said a few minutes back about hash functions. We have SHA-512 algorithm, right? Or even SHA-256 algorithm. These are the classical hash functions. Even they can be used to address this PQC, especially for the hash-based digital signatures. So if you notice, SLH DSA uses signatures using the hash functions, Merkle trees, and one-time signatures. Again, if you notice, hash functions, we know. Merkle trees, especially those who are familiar with the blockchain, they would be knowing the Merkle trees, right? So Merkle trees are used in the case of DSA. So let us see what actually happens. So Merkle trees philosophy is this. At the leaf nodes, you will have the data items. This is your root node. This is your root node. This root node is hash of all hashes, right? This root node is hash of all hashes. So these are all, the data points, right? So you can see here at the leaf, data 1, data 2, data 3, data 4. So first you apply the hash of data point to get hash 1. Similarly, hash of it, data 2, hash of data 3, hash of data 4, right? So since it is a one-way function, anybody can have a hash. Anybody can create a hash from their data point. But whoever is having the hash, they cannot get back to the the data point, because hash is a one-way function. So having a data point, calculating the hash is easy. From the hash, calculating the data is not possible because it's a one-way function, right? So take the data element, create the hash. Now you have a hash 1, hash 2, hash both of them to create hash 1, 2. Similarly, hash both 3, 4 to get this hash. Now I combine 3, 4 and 1, 2 to get my hash 1, 2, 3, 4. And this is my root node, right? And this is the root node. I'm calling it as hash of hashes. This is the concept of Merkle tree of hashes. This we have, those who are familiar with blockchain, I think, they would know about this. Now, where this is being used or how it is used in the public key PQC algorithms. If you notice, these leaf nodes are keys. These root nodes are key, the leaf nodes are keys, and this is my hash of all hashes, right? Now I create hash of K0 and K1 at level 1. Similarly, hash of key 2 and key 3 N11, hash of K4 and K5 as N12, hash of K6 and K7 as N13. Again, hash of these twos, hash of these two hashes. Finally, hash of these two hashes, right? This is the Merkle hash tree. Now, how I will use it for the purpose of hash-based signatures? What I'm going to do, I have to, my digital signatures, first of all, I have to sign on a message. So for that purpose, what I do is I take one particular public key from the tree, sign the message using the corresponding secret key of the public key, right? Secret key of that particular public key. Then I will concatenate the signature along with the public key and its Merkle proof so that receiver would verify my public key and the Merkle proof. How this happens? Let us take one example and see. Imagine I have a Merkle tree where I have totally 8 signatures, right? If you see here, the leaves, I have, this is my public key, private key pair, X0, Y0, X1, Y1, and so on. Totally 8 key pairs I have, right? Now, hash of this public key is A0. Hash of public key Y1 is A1, right? Like that, I have totally, in this case, totally 8 hashes of their public keys. Now I am combining at level 1, hash of first public key and the second public key, I am combining at B0. Hash of second one and then third one, I am combining it as the hash 2 and so on, right? My overall public key is the hash of hashes. Okay, so now at the leaf nodes, I have public key, this is public key, and this is private key pairs, right? So totally 8 signature pairs I have, and I have totally hash tree with the root as hash of the hashes. Now, how do I sign it? Now, imagine I have already signed with 3 signatures, so I am using the 4th one. What is my 4th one? So this is 1, this is 2, this is 3, this is my 4th one, right? To sign, what I will use? I will use private key for signature purpose. So sign with the help of private key. What is private key? Private key is, your X. X is the, the private. So use X for signing purpose, signing of the message. So my signature is S3. Once I signed, I will send the message to the Bob. What are all the things I'm sending? I'm sending my signature, S3. I'm sending my message, and then I'm sending my public key. And not only that, I'm sending A2. What is A2? A2 is the hash of my previous public key, right? A2 is the hash of public key, a previous public key. Then B0, which is there in the chain, and then C1, which is there in the chain. I will send it to Bob. Now what Bob will do? Bob will take my signature and verify whether Y3 is the one which I have used, or Y3 is my public key or not. How do he check? He check it by cross-checking through this particular chain of hashes. So what he will do? He will take A2 and he will take my Y3 and find out by hashing the Y3, he will get A3. He will combine A2 and A3 to compare B1, right? And B1 and B0 he will take to get C0. And he takes C0 and he has now C1 that I'm sending to get D. So he gets D, and then what I have sent in the chain, if both are same or not, that he will verify, so that my public key signature is very correct or not, or whether I am authentic or not, that is being verified. If you notice, this entire verification, signature and verification process is held with the help of hash functions rather than the classical public key, private key pairs that are coming from RSA and Diffie-Hellman. The strength of this is because of the hash functions, which are not possible to invert, meaning taking the hash and finding the original data item, even by a quantum computer, right? So that these are the two variants that one needs to know essentially in terms of the NIST standards, FIPS standards. To quickly come to the point of PQC being in action. Now at the moment, the almost majority of these TLS implementations are being replaced with the PQC compliance. You can see that this is the typical TLS handshake that happens in HTTPS protocol, right? In that handshake, you can see the KEMs being added on top of your regular DSA, meaning digital signature algorithms, and the public key encryption algorithms, right? Now, one has to, those who are working or interested to work, we need to focus on the migration of PQC, and it should happen in a very gradual multi-year. It's a multi-year process, because the more the shorter the time to a quantum cryptographically relevant quantum computer, it is sooner the better, right? How do we do that? Of course, we need to move from a post-quantum unaware scenario to post-quantum enabled scenario. In that process, we need to move in this technology readiness levels from being unaware to just being aware, and make our the systems, all cryptographic libraries get ready for replacement, and then finally being enablement. What I suggest is, recently Meta has released this particular migration framework for post-quantum cryptography migration. Those who are interested can actually look at that. So they have given several the steps, or rather layers of migration strategy, starting from prioritization of the migration process. And in that process, they have given topmost priority for the applications that are using public key encryption algorithms, similarly key exchange algorithms. Similarly, if you look at, even in this high priority scenario, imagine that libraries or built-in libraries, or that are dependent on external libraries, the challenge would be the complexity would get increased. Now, again, whenever we are looking at the migration, we need to look at the different types of attacks, including efficient attacks and offline attacks. Efficient attacks meaning ability to break these, the algorithms with ability to break this, asymmetric algorithms with the help of, SHAR algorithm or even a Grover algorithm kind of a thing. Offline attacks meaning, the attackers can collect all currently communications that are happening with the, in a digital world, and once the cryptographically relevant quantum computer comes, they will break it. Such type of attacks are called offline attacks. Rather, they can also called as harvest now, and decrypt later. Okay, so such type of attacks also are there where people have to make a strategy. Similarly, whenever we are trying to replace or migrate, we need to have a strong cryptographic inventory. The reason is that replacing the cryptographic algorithms is a regular process. We need to know each algorithm gets deprecated during the period of time. So take an example, message digest algorithm was deprecated even in 2005 itself, right? That has to be replaced with the SHA algorithms. Like this, every encryption algorithm needs to be replaced, right? We need to know what are the cryptographic inventory that we have and that need to be replaced, right? In that process, we need also to see the dependency levels. If at all there are external dependencies, the challenge would be more, right? So these are the challenges which I think I have already mentioned. Essentially, whenever we are going for this migration, we need to focus one particular concept in mind called crypto agility, which is the ability of the systems to switch cryptographic algorithms without any kind of a major redesign in the existing protocols and products, right? So, and for that purpose, people are suggesting to go for hybrid systems, not to just like that replace the classical algorithms, rather multiple layers of classical and PQC encryption algorithms, right? This is the migration timeline that is given. Of course, I have given the source, which those who are interested can have a look at it, right? These are all quickly some of our contributions that in the area of quantum computing, that our researchers at VIT we are working on. Various international journals we could work on quantum computing, quantum inspired computing, quantum inspired human cognition, then about quantum machine learning, right? Deploying the quantum computing principles through cloud-based environments, then about homomorphic encryptions to the quantum fully homomorphic encryption schemes. Then recently we have worked on the analyzing the encrypted traffic with the help of quantum machine learning algorithms, right? These are all some of the works that our team is working in our research labs. With that, I would like to conclude my presentation. Those who are interested can write to me over my email or connect with me in the LinkedIn. Several of my lectures are already there in the YouTube channel. Have a look at them. So any queries, I would be happy to, answer.
Sir, thank you very much, sir. This is Murli talking. I will take up the questions and I'll forward it to you, sir. So since that time is up and the bus is leaving, so I'll. Sir, am I audible?
Yeah, you are audible. I'm seeing some
yeah.
questions coming in. Okay, sure.
No, I'll take up the questions and I'll forward it to you. You may please give a response so that I will share that to the audience through the message. Yes,
Definitely.
sir. Yeah. Thank you very much, sir. And the vote of thanks will be preceded by Mrs. Annapurna.
So on behalf of the organizing committee, I express our sincere gratitude to our esteemed speaker, Dr. Aswani Kumar Cherkuri, for delivering such as insightful and informative session on post-quantum cryptography algorithms and migration. Your expertise, valuable perspectives, and engaging presentation have greatly enriched our understanding of this important emerging field. The knowledge you shared will on the topics post-quantum cryptography algorithms, lattice cryptography, LWE problem, hash-based cryptography, PQC migration strategy. So will undoubtedly benefit all the participants. Once again, thank you so much, sir, for spending time with us. Thank you, sir.
Thank you, madam. Thank you.
Thank you very much, sir. Despite having your busy schedule, you spared us and you gave your valuable time. I still remember that. Yeah. Thank you very much, sir.
Thank you, doctor. Thank you.
Online.